Myself Ajay Kumar. Today our topic is application of service-oriented architecture to distributed simulation. And the introduction is service-oriented architecture in an architectural approach in which systems components expose functionality and data in the form of services that may accessed by other components using standard basic technologies. And SOA is particularly applicable to architecting systems of systems. It focuses on how we applied SOA in major assets such as simulation algorithms, visual tools, and data archives in order to increase our flexibility and speed in applying these assets to solve problems for our sponsors. The Federal Aviation Administration is currently beginning the apply SOA principles and technologies to the National Airspace System. NAS is the system. And literature survey. In the early phases of SOA transition described in generic SOA roadmaps, an organization is assumed to be starting with an environment in which different systems are interconnected with unique interfaces. Transition to the SOA in such as environment begins with replacing point-to-point unique interfaces with industry standard protocols and data representation formats for interconnecting systems. In SOA, interfaces between systems are defined in a standard manner in terms of services that each system offers to the other systems. Two protocols are analyzed according to certain characters such as time synchronization based and multicast and broadcast and based mobility aware and QA quality of service and real-time capability. In addition to applying industry standards, an organization may have developed their own local standards for interconnecting systems. Their conclusions highlighted some challenges that still need to address in future work to enable the implementation of a highly efficient MAC protocols. And the main contributions of the paper are listed below. Serving as a master interface control document ICD for the organization. In a traditional system of systems architecture, if multiple systems need to interact with the system operators, identify and describe the problems that can occur in each topology, and review and discuss the available in the literature, highlight their strengths and weaknesses. And problem analysis. The issue of performance impact of SOA technologies is frequently raised and undoubtedly important in many simulation domains. This section of a paper addresses this issue in some depth. As discussed above, use of XML is fundamental and pervasive in current SOA technology because XML emphasizes generally and human readability over compactness. There is a frequently expressed concern that the XML verbose and several different approaches are possible to assess the performance impacts and limits of certain technology, including analytical methods and simulation and modeling and measurement of candidate implementations. And service consumers, service bus and service interfaces and service implementations. Proposed solution application based on the performance experiments described above as well as our initial experience in utilizing web services to interconnect simulation components, we accept that technology is likely to meet our performance needs our interconnecting components that are running real-time simulations. Methodology. One of the most basic aspects of the SOA transition is use of web services to allow different systems to access data and functionality available from other systems. Simulation independent services. First, we consider services that provide data independent of whether a particular simulation is running. We refer to these simulation independent or static services. This class of services might include access to data archives or arithmetic functionality. Web services in this category include adaptation data service, weather data service.
Resources and technique. We are applying a web service in area of simulation control. We define, manage and assess service for this purpose. The interface contains the following methods. Launch, execute a simulation application, creating a new simulation run. Initialize, perform any necessary loading of data or setup prior to the commencing the simulation run. Go commence the simulation. Starts the simulation clock. Pause the simulation run. Resume a paused simulation run. Get status, returns information about the current state of simulation run. This is the diagram of service oriented architecture. Terminate all the simulation run and release all the resources. To date, we have implemented one assist manager that provides the manage assist service interface. Assist manager is a web service in front of our central simulation manager. CSM is a legacy simulation management capability which supported by the many different types of CAASD simulation assets. Process Manager enables web services based simulation control for all these simulation assets. Solution: the application of service-oriented architecture to distributed simulation offers a robust and scalable solution for modeling and complex systems and scenarios across the various domains. SOA, a design paradigm that emphasizes the uses of loosely coupled and reusable services, provides several key benefits in the context of distributed simulation. Furthermore, SOA facilitates interoperability and integration, allowing diverse and simulation modules or systems to interact seamlessly, enhancing the collaboration and data exchange. Additionally, SOA promotes the reusability of simulation and service, reducing redundancy and development time for similar simulation. This approach not only enhances the efficiency of the distributed simulation but also supports the integration of real-time data sources and the external services, making it adaptable to evolving simulation needs. The adoption of SOA in the realm of distributed simulation revolutions the way we model and analyze the complex system. At its core, SOA promotes a modular and decoupled approach to the system and design. In the context of distributed simulation, the means of breaking down the simulation into discrete, self-contained services that encapsulate specific functionalities. These services can represent various aspects of the simulation, such as environmental conditions, entities, behaviors, or data storage. This modularity brings several advantages. Firstly, it simplifies the development process. Teams can work on individual services independently, fostering parallel development and reducing the bottlenecks. Moreover, it enables the dynamic scalability, allowing services to added or removed as needed, making the simulation system adaptable to varying computational requirements. This is the graph of track message receive rate with increasing number of producers. Another critical aspect of SOA in distributed simulation is its emphasis on interoperability and integration. In a distributed environment where different simulation components may be developed by different organizations or used different technologies, SOA provides a common framework for seamless communication. Services communicate through the standardized interface, making it easier to integrate various simulation modules even if they are built using different programming languages or platform. This interoperability promotes. This protocol supports efficient one-hop or multi-hop broadcast services on the control channel, which provides a smaller rates of access collision and merging collision caused by node mobility. This is the graph of CPU load with increasing number of producers. Validation for the application of service-oriented architecture to distributed simulation involves a rigorous assessment of whether SOA principles and practices are suitable for the specific requirements. It is essential to define goals for the simulation such as scalability, interoperability, and efficiency, simulation architecture, and its alignment with the SOA principle. Conclusion. Furthermore, SOA emphasizes on loose coupling and standardized communication protocols as the potential to streamline the development process and reduce the integration complexities. SOA enables greater flexibility, scalability, and reusability within the distributed simulation environments. Service-oriented architecture has demonstrated its potential to significantly improve the development and integration. In conclusion, the application of service-oriented architecture distributed simulation has proven to be a transformative and highly effective approach. SOA enables the greater flexibility, scalability, and reusability within the distributed simulation environments.